really get it. Turn up right after.
Welcome and good evening, or good afternoon. I'm Meredith Vaughn. I'm the Associate Director of the Center for Research in Mathematics and Science Education here at San Diego State, or CRMSE, as we like to refer to ourselves. And I'm also a science educator in the School of Teacher Education. And I'm really pleased to welcome you to our distinguished lecture this evening. CRMSE's Distinguished Lecture Series brings together mathematicians and science educators to come to our campus to engage with us as faculty and students and teachers and community members. And so we're excited to have you all here, and we're especially excited and thrilled to welcome Dr. Helen Quinn. Dr. Quinn is a professor emerita of physics at the Stanford Linear Accelerator Center and also a member of the National Academy of Sciences. And then in addition to her distinguished career as a physicist, Dr. Quinn has long been interested in issues of education. As a member of the National Academy, she chaired the Board on Science Education. She also chaired the National Research Council Study Committee, which developed the framework for K-12 science education, which many of you know lays the groundwork for the next generation science standards. And among many other things, currently she's working with Stanford's Understanding Language Project, where she chairs the science work group, and recently produced a white paper with Oki Lee and Guadalupe Valdez titled Language Demands and Opportunities in Relation to the Next Generation Science Standards, or ELLs. So this evening we are thrilled to hear from Dr. Quinn as she shares with us how science classes can contribute to language learning and how language learning can contribute to science classes. Please join me in
yesterday. There will be some repetition and some of the slides you've seen before. I don't think it ever hurts to hear things twice, so that's okay. But for those of you who weren't at my talk before, you'll need that as context when I'm talking about when I talk about science learning. Secondly, I have a very specific viewpoint on language learning. So before I go into my slides, I want to talk a little bit because I think there is more than one model out there for what it means to learn language. And I'm very much in the camp of Guadalupe Valdez at Stanford, which says learning language is about learning to do things with language, not about learning language structures or vocabulary. You need language structures and vocabulary in order to be able to effectively do things with language, like express your ideas, or argue from evidence, or describe to somebody else what you've observed. But each of those language tasks is for a purpose, and the purpose is more important than the language structure, as long as you can achieve your purpose in communicating what you wanted to communicate. That, and as a language, I'm a language learner myself because I'm still trying to learn Spanish, and from my own experience, it's much more important that I can express something than that I express it correctly the first time I try. So the idea of, okay, students must speak in full sentences, for example, actually interferes with the expression of ideas. And so and English speakers don't speak in full sentences when they're expressing half-formed ideas either. So thinking about what it is we want our students to do with language, and then supporting the students whose language is weaker to be able to do those things and to contribute to a classroom discourse where student talk is an important part of student learning. That's the issue I'm talking about today. Not how do you get them to have correct grammar or to increase their vocabulary, although they will, as they practice, get closer and closer to speaking correct English and to using a richer vocabulary. Okay, so that's a preface. Now let's go into the kind of science teaching I'm talking about, which comes out of the framework. The idea is that science learning should have all three of these dimensions. One dimension is, what do scientists do? What are the science and engineers for that matter? What are the practices they engage in as they do their work? Why do students need to know that? partly because only by knowing that can they know the difference between knowledge that is science and knowledge that comes from other kinds of traditions and cultures and sources. Secondly, because by engaging in the practices, they're engaging in work that allows them to undergo the process of conceptual change to get from their naive conceptions of the world to a conception which more fully integrates the learning that they're achieving in their science classrooms. It's that integration of new ideas into your own conceptual framework, which is real learning, as opposed to artificial learning, where you layer it on top, and both concepts are living there, and the student, when asked to solve a problem, refers only to the knowledge that, and conceptions of the world that they had before the learning, because the learning is just a layer, like the frosting on a cake, that's smeared on, but not actually integrated into their way of looking at the world. So, then having defined these three things, and I'll tell you a little bit more about what they are, the standards that are the next generation science standards, we, the people who wrote the framework on which the standards are based, said it won't work unless the standards really have all three of those dimensions in the standards. So here's one example, right? So for grade 3, plan and conduct an investigation. That's a practice, right? To provide evidence of the effects of balanced and unbalanced forces, stability and instability as a cross-cutting concept which applies across all disciplines, understanding the conditions of stability and instability of systems. And finally, on the motion of an object, the core idea of physics that forces make things move, change the way they move, understanding and beginning to understand that at a third grade level, which won't be full understanding of Newton's laws, is a step towards the understanding of what you can build across the many years in school. So that three-dimensional notion that these pieces have to be integrated in instruction is very important. Which means students are engaging in these practices and using the cross-cutting concepts as tools to solve problems. That means there's a lot of talk in the classroom. Student-to-student talk, not just teacher-to-student talk, and student response to teacher. And so the classroom, being a discourse-rich environment, is a language-rich environment. And therefore, thinking about how to support language learners to both survive, to learn science, and to learn language in that environment is a valuable way of addressing how do we really use this time most effectively for students. Okay, so why three dimensions? Here's a quote, again I gave it yesterday, from Henri Poincaré, and it's there in French for those of you who read French, and it's there in my very rough English translation for those of you who read English only. But the point is that science is not just a collection of facts. That's no more than a pile of stones. So they say science is a construction based on facts, yes, but it's a construction of ideas, of theories, and of explanations. And that process of construction, like building a house, requires more than just the materials to build the house with. So if you think of the three dimensions, so students must build their own three-dimensional knowledge structures, and in order to do that building, get from their preconceptions to the science conceptions, of course they need the knowledge, they need the core ideas of the disciplines, they need some introduction to the ideas that scientists have developed over hundreds of years, but in the context of solving a problem where that knowledge is useful. And next they need the tools and practices and the experience using them. That's the science and engineering practices. You can't build a house if you don't have any tools. And thirdly, you can't build a house unless you know what a house is. Right? You have to think, you can have all the wood in the world and all the tools, and you will not build a house unless you have some idea of where you're going as you try to put those pieces together. So the cross-cutting concepts are the metacognition pieces, the concepts that you need that provide tools for where do I go with these things? And that is why it all needs to come together in the learning so that the students really can do this constructive learning in the head. Here's the list of practices. All of them are discourse rich. The ones in red are ones that generally in inquiry-based classrooms have, I think, been underemphasized. So students for years have been saying, people have been saying, you should be doing hands-on science and students should be investigating things. But it's no good investigating if you don't analyze what data you got. And you don't ask, how does that data correspond to the idea you had that was an explanation for what you thought would happen, or the model you had as to how that system functions. So the analysis parts, which are the discourse parts, are much more stressed in this view of science education. And therefore, language and language challenges become more important to think about in everything you're doing in the classroom. Not that they weren't important before, but if you're asking students to talk to students, then you have to support an atmosphere in the classroom where all students' voices are important. The inclusion that says, even though I expressed my idea without being able to say it right because I don't have enough language to say it right, that idea is part of the building of consensus and ideas in the group. How do I support the student whose language is weakest to contribute? He may have the best ideas about the science, but he may not be able to express them. So figuring out how to support a range of language ability along with a range of science ability, this is a challenging task for teachers. But it's equally important to think about the language aspect of it in order to teach the science, as it is to think about the science aspect of it in order to teach the science. So supporting the language learner actually turns out, since no kid arrives at school talking about science like a 12th grader even, so every kid is a language learner in the science classroom. And things that you do to support language development in the science classroom support all students, not just the ones who happen to be labeled as language learners. Of course, the ones who are labeled as language learners may need a little more support. But the idea that thinking about and supporting language development in the science classroom is an important part of teaching science is one of the ideas underlying my talk here. Okay, here's the list of cross-cutting concepts. I'm not going to spend a lot of time talking about all of these, but each one of these, I think of it as a generator of questions. If I am thinking about a new problem and I'm trying to solve this problem, I say, okay, what's my model for this system that I'm looking at? What is the system? How do I model it? What are the mechanisms of cause and effect? What are the patterns that I'm seeing? How do I explain those? So each one of these concepts suggests questions I can ask in order to solve whatever problem I get to. And that's the reason why they're very important to stress. In science education generally, we've sort of under-stressed these things and stressed the particular pieces of science knowledge we're trying to teach. But in fact, in order to take those pieces of science knowledge and apply them in the context of a new problem, these ideas and the questions they generate are very important tools for learning too. But questions are language too. So even being able to ask a question as to, what did I notice here and what patterns are happening, that's a language task. Right? And to communicate to others, well, I noticed this and I observed that and I think this pattern might be related to that. Those are all language tasks at the same time as their science learning tasks. So figuring out how to do this complex job of supporting both the language and the science is something that takes teachers' practice. There's several groups that are working on this. I point to the group from the Inquiry Institute at the Exploratorium, for example, in San Francisco, who've been working with kids in the Santa Rosa School District. And their work is showing that not only do these methods support science learning, but they really support language development and literacy development